We're all familiar with the crowning achievement of human exploration of space, visiting the moon. These trips were and continue to be tremendously inspiring, and their scientific value also continues to grow with ongoing analysis of the 380 kilograms of lunar rocks and soils that the astronauts brought back. Now, since Apollo, there have been solid achievements in human exploration with shuttle and space station programs, but astronauts have been constrained to low Earth orbit, only about 250 miles above the Earth. And the shuttle program is now defunct, as chronicled in an award-winning book by Professor Margaret Dean of the English department. NASA also inspires with its so-called great observatories. The most famous of these space telescopes is Hubble, shown on the left with a remarkable image of the Orion Nebula, which incidentally is visible tonight in the night sky, in Orion's sword. But others have viewed the universe at different wavelengths, and NASA is about to launch Hubble's successor, the James Webb Space Telescope. What's somewhat less well known is that NASA has, in fact, been exploring our solar system quite vigorously over the past few decades, just not with humans. This diagram shows all the robotic spacecraft missions sent out to the solar system, performing relatively detailed reconnaissance from Mercury all the way out beyond Pluto. Some spectacular results everyone may have heard of include our first close-up views of Pluto just a few months ago, the rovers on Mars, the discovery of rivers formed by liquid methane on Titan. Now, although we may be familiar with the planets, there are billions of smaller bodies in our solar system, and I'd like to talk about some of these, the asteroids. And the first thing we might ask is, what are asteroids? They're basically small, rocky bodies that orbit the sun. They're interesting because they're the leftovers of planet formation. So if we want to know how the Earth formed, asteroids are actually the material that are left over out of which the Earth formed. And where in the solar system are asteroids? They're shown and color-coded on this animation that isn't working. But if it were, you would see that most asteroids reside in the main belt, which is between Mars and Jupiter. There are a bunch of near-Earth asteroids that orbit near the Earth, and then a large number of asteroids are further out. We've only seen a handful of asteroids close up. The montage to the left shows several at the same relative scale, while the largest asteroid series on the right is shown at a different scale. Most asteroids are potato-shaped, and their surfaces show a lot of impact craters, kind of indicating a long collisional history. And we've gotten very close to two small near-Earth asteroids. NASA's NEAR mission landed on Eros to the left here in 2001, and a Japanese mission landed on and returned microscopic samples from an even smaller NEA, Itokawa, in 2005. Notice how blocky Itokawa is. It's actually a rubble pile rather than one coherent body. And it turns out that different asteroid compositions cluster to some extent at different locations. The most common and closest to us are made of normal rocky minerals. A little further away are asteroids composed of clay. They formed with a significant water component. But at the outer edge of the main belt and in the Trojan swarms, which you didn't get to see on the animation, are asteroids whose compositions we just don't know. And here at UT, we've studied these distant bodies in detail. A recent PhD graduate, shown on the lower right, used large telescopes in Hawaii to study the clay compositions, and we discovered a class of these asteroids that retain their original water component. They remain too cold for the chemical reactions that form clay from rock and water. And I've also spent much of my career observing these Trojan asteroids, which share Jupiter's orbit around the sun. There have been recent suggestions that the giant planets have actually moved around since they formed, and the Trojans are a key population for testing this hypothesis. NASA is currently considering a robotic mission to the Trojans, and I'm on the science team, which is a lot of fun for that mission. Coming closer to home, that same animation that's not working again, you would see thousands of near-Earth asteroids orbiting the sun in Earth's proximity. Because they come close to planets, they can only exist in these orbits for about 1 million years before they crash into a planet or into the sun, and then they're continually replenished from the main belt. These are interesting scientifically for understanding the primitive compositions and surface physics in low gravity. They also pose a potential hazard. Asteroids do impact the Earth, even Tennessee. There are actually 2 large impact structures in Tennessee. And some people think that mining of asteroids may someday be fruitful as well. Now, at UT, we've been mostly interested in surface physics of NEAs. A postdoc here discovered this small asteroid that rotates so fast that the centrifugal forces are stronger than gravity, so it should just fly apart. But it turns out that weak cohesive forces between very small grains provide a strong enough network to hold it together. And we've also discovered water molecules on NEA surfaces. These are formed by very fast collisions of hydrogen nuclei, in other words, protons coming from the sun. It seems that they form or are retained preferentially on larger asteroids, and NASA's recently funded us to continue some more observing to gain a better understanding of this process. And to provide an even more detailed analysis, NASA is about to launch the OSIRIS-REx mission to return a sample from a near-Earth asteroid. And I have the great fortune of being on the science team for that mission, which has been really exciting for me. Our target asteroid Bennu is about 500 meters in diameter, shown here with the Golden Gate Bridge for scale on the lower right there. The spacecraft launches in just a few months, September 8th of this year. This is a timeline of the mission. It'll fly by Earth late next year, then get to Bennu towards the end of 2018. We spend over a year characterizing Bennu to select a sample site, then collect the sample and bring it back to Earth in 2023. Now, it turns out this spacecraft isn't actually going to land on the asteroid. Instead, it'll collect the sample using this 3-meter-long arm. Loose surface material is blown into the sample chamber by discharging canisters of compressed nitrogen gas. So I hope I was able to convey that there's a lot of scientific interest in the study of asteroids for understanding the origin and evolution of the solar system, and that there's a significant program of asteroid research here at UT. Thank you.